Hello, Dr. Zeilinger. Can you hear me?
Yes, I can hear you very well. Thank you so much for organizing this and inviting me.
Yes, and yeah, it's a pleasure to have you at our seminar series. Likewise. And
Um, all right,
before,
should I try and share the
yeah,
slide?
yeah, we can test that once.
I'm trying this.
Yeah, I can see your screen now.
Okay. Um, and okay, right? This
Yeah,
works.
yeah,
Okay, very good.
yeah. The, for your information, like this seminar is being live streamed on YouTube, and
Mhm.
all the participants will be on YouTube. And any questions they ask, I will direct them to you.
I
And
see. Okay.
yeah,
Yes,
so
that's good.
yeah. And how do you like to be asked questions? Like, is it fine if they interrupt you at the middle or is it at the end? How do you prefer?
For me, both is fine. What do you
Okay.
usually do?
We leave it up to the speaker, but mostly the audience ask questions at the end. So
Yeah.
yeah, that's how it usually is. But yeah,
Okay, good. Yeah, I mean, if you see a question that you find, is relevant for asking in between, then feel free
yeah,
to
yeah,
interrupt.
yes, yes. And my advisor, Dr. Malakopoulos, he'll be also on the stream attending the
Mhm.
talk. Yeah, couldn't. Yeah, we have some time before we can start. Like we can start right at 12 over
Okay,
here.
sounds
So
good.
yeah,
You just let me know.
yeah, definitely. Yeah. Dr. Zeilinger, like I just have a question.
Yes,
I see that you're one of the organizers for this L4DC, which
yes.
is very, I guess it's very well known these days for combining controls and learning and all of that. Now, like what was the motivation behind starting such a conference? Like, what was the big picture that you guys had in mind when you came up with something like this?
Yeah, so really the idea came from George Papas and Ali Jababai when they discussed and realized that um, looking at the intersection has sort of specific challenges that are often not covered or don't get enough attention in either discipline. And so the motivation was really to create this new venue, also for young researchers, right? To highlight the contributions at this intersection. Um, and I think it's we're seeing that it's really worth doing that because in both of the communities, of course, there's so many topics where this is just sort of one part of it. Whereas if you go to L40C, then pretty much everything is relevant. And I think those smaller conferences are, my PhD students very much enjoy that they go and just, yeah, everything is important.
Yeah, yeah, definitely. Yeah, I've been to CDC, and yeah, I've never had the chance to attend L4DC before. But yeah, like that'd be nice to see people from both controls and people who primarily work on this learning and AI community merge. And yeah, it'd be
Yeah.
nice.
Yeah. Yeah. I mean, the next one is in the US, so maybe that's more convenient for you
Yeah,
than the last one in the UK.
yeah. Hopefully, we'll get in something. Yes. Oh, yep. Sorry, my internet had a disconnection. Yes, we can get started now. So first, I'll just give you a short intro, and then we can take over that from there.
Sounds good.
Uh, Hello, everyone. Welcome back to this week's DDLC seminar series by the Ideas Lab at Cornell University. This is Nishant, and today's talk is going to be about learning and optimization-based control, guarantees, performance, and computation. And it's a pleasure to introduce today's speaker, Dr. Melanie Zeilinger, and she is an associate professor at the Department of Mechanical and Process Engineering at ETH, and she's leading the Intelligent Control Systems group at Institute for Dynamic Systems and Controls. And she received her diploma at University of Stuttgart and her PhD at ETH. And from 2011 to 2012, she was a postdoc fellow at EPFL, and from 2012 to 2015, she was a postdoc researcher and a Marie Curie Fellow in a joint program with UC Berkeley and the Max Planck Institute for Intelligent Systems. And in 2018 to 2019, she was a professor at the University of Freiburg, Germany. Her awards include the ETH Medal for her PhD thesis and a Marie Curie International Outgoing Fellowship and an SNF professorship grant. And she's one of the organizers of the well-known Learning for Dynamics and Controls conference, and she also organizes workshops in CDC and many more workshops in other conferences. And Dr. Zeilinger also contributes to a lot of on editorial boards in various conferences, and her research and interests include learning-based control as well as distributed control and optimization with applications to robotics and human empathy. And without further ado, I'd like Dr. Zeilinger to take on now.
Thank you so much for the kind introduction, and thank you for the invitation. It's a pleasure to speak at this seminar series, and I'd like to thank you all for attending, spending your lunch break with me if you are in sort of the Eastern time zone, or maybe your early evening if you are in Europe or some other time. So, Nishant already said, so I want to provide our perspective on the combination of learning and control, in particular, taking an optimization-based viewpoint, where we in particular discuss how we can achieve guarantees while not overly compromising performance, and also addressing computational challenges. Before I begin, I'd like to mention that this, of course, what I'm presenting today is the work of excellent postdocs, senior scientists, PhD students. I will not mention them as we go forward, but you'll see their names in the references that I put up. And of course, there's many things that have come together over quite a few years. So here you see the entire team. So I'd like to begin with a slightly broader motivation for what we want to look at. So we're interested in thinking about control to advance autonomous systems that are particularly challenging due to either having very complex dynamics or they're acting under complicated environments, unknown environments, which leads to difficult constraints. Maybe there's even humans that affect the system, or which may have to solve difficult tasks that we often have difficulty describing, or that are even unknown a priori when I start the system. So from a control point of view, that leads to a range of uncertainty that I need to address when trying to control such a system. And again, what we're looking for is to provide some form of guarantees under these uncertainties. So in our research, I think we're taking two different angles on addressing this. One line of research is to develop methods that can account for uncertainty. So here we're thinking about robust or stochastic control and estimation methods that take into account this uncertainty, where it's important that these are high performance methods. So we don't want to overly compromise performance by accounting for uncertainty. And then the second line of research is thinking about how can we actually reduce uncertainty? How can we learn more about the system? So we're thinking about sort of coming from dynamics, constraints, and tasks. So we're really thinking about learning better models of the dynamics, of the constraint descriptions, and of the objectives that we try to achieve. And of course, if I am now in that learning setting, it becomes particularly important to think about safety. And so for the talk today, I want to entirely focus on the second line of research, so thinking about how we achieve learning while ensuring safety. And I'll assume that we have tools available that give us robustness or stochastic treatments. I won't focus on that today. Okay, so going forward, I'll address those three topics. And what we want to achieve is, of course, a high-performance controller that achieves guarantees. So we're looking for a good trade-off there. And because we want to think about safety, I will build on optimization-based techniques. And when we use optimization, then I think it is particularly important that we also add a third bubble here. And this is we need to look at efficient computational methods for the things that we're proposing so they're actually practically feasible and can be implemented in real time or on board. So it's really that we're looking for a good trade-off between achieving those three objectives. Okay, so I'll go through the talk in this order, talking about learning a model of dynamics, constraints, and objectives. But before I get to that, I'd like to define for you what I actually mean with safety. Because of course, there's many things that we could mean. You could think immediately about stability. But this will not be in the focus. I'll define safety slightly more broadly as constraint satisfaction. So we assume that safety constraints are specified on my states. And so for most of the talk, I will build on a discrete time dynamical system description here. Standard control notation, X is the state, use the input, and K is the discrete time index. And then I have state constraints that define mostly my safety constraints. And of course, I also have input constraints that are coming from sort of limited actuation in the system. And that's sort of my minimal requirement to achieve safety. And it's quite a flexible safety description, I would say. And then, of course, you can add on top other requirements if you then wanted stability or something else. So when we want to achieve safety in the form of constraint satisfaction for all times for a dynamical system, then we commonly achieve this by building on the tool of control invariance. So here is our classical definition of control invariance. So a set S is said to be control invariant if for any initial condition in the set there exists inputs in my input constraints that keep the state in the set. And then, of course, if I design such a control invariant set so that it's within my safety constraints, then I can guarantee safety at all times because I know also in the future there will exist an input that keeps me inside of that set. So it's quite a powerful concept, but of course, getting large control invariant sets is difficult. They're hard to compute. Coming from a predictive control background, of course, we know that we can also reformulate that implicitly and get sort of a good approximation of a control invariant set by writing this down as a forward planning problem. So we can build on a potentially conservative control invariant or just invariant terminal set under some controller, and then say, well, any state is now also safe, we're in the control invariant set, if I can find a trajectory satisfying all of my constraints that ends up in this terminal set. And so I'm now implicitly defining my safe set as all X for which these constraints are feasible. Of course, this is the backbone of all predictive control theory and how we actually get constraint satisfaction there. But it's interesting that this has also now been more and more extracted as a general safety mechanism independent of directly implementing a predictive controller. So this has been done in so-called multi-trajectory MPC in the form of a safety filter. Later on in this talk, I will use it to achieve safe exploration when I'm talking about constrained learning in particular. But I do want to briefly spend some time on that idea of a safety filter, because of course that is one tool that would allow us to add safety guarantees to any learning controller. So just very briefly, what is the idea? Let's say that I have some system and I have a controller. The safety filter would be an additional component that doesn't know about the control policy, but just takes the proposed action and the state, and then has to verify if that action can be safely applied, meaning that I can guarantee constraints also going forward. And if that's not the case, then of course, the safety filter has to propose an input, a safety ensuring control action. Of course, we can now think about that problem building on the tools of control invariance. And this has been done, I think, mainly in 3 directions. Of course, thinking about control invariance and computing these via reachability analysis, control barrier functions have become extremely popular. But also, now that we have seen this idea of safety as a planning problem, you can also write down a predictive safety filter. There's many more that I'm not listing here. Techniques relating to reference governors. There's also different terms than safety filters like runtime assurance, etc. So I'm just highlighting those 3 as 3 main categories that we've in particular thought about. And we've tried to put them in perspective in this recent Control Systems Magazine article. And we've also given a tutorial at the L4DC last year that you can find online if you want to hear a little bit more about safety filters. So if we now write down a predictive safety filter, we can directly take these constraints that we had before, which ensure safety from some current state. But now we're going to add our safety filter objective and say, well, we want to plan a safe trajectory, but we also ideally want to match the proposed action. And this is the same objective that we also commonly use in control barrier functions. So if I apply the optimal U0 from that problem, then I know this is always safe. So a safety filter is nice as that it could be combined with any other learning controller. The predictive safety filter formulation in particular is nicely scalable. And it allows us to build on everything that we've learned about predictive control. We can do robust stochastic formulations. We can improve this by adding learning to it. We can actually also add additional conditions if we not only care about constraints, but also for stability, because we want some smoother behavior. We can add stability constraints as something that we've recently done. You can draw connections to CBF, so we can do predictive CBFs, etc. So I could give an entire talk on this. I've decided not to do, but I just want to sort of highlight that this is also an extremely nice and powerful direction. Here's one of our early videos where we applied this to our miniature race car. And because it really doesn't need to know about the policy that you want to apply, you could also use this as an assistance system. And this is actually what has then been implemented by a team at Bosch, where they use the safety filter as a driver assistance system and then put it on their safety vehicle. So here it's really just doing lane keeping independent of what the driver is doing. And so it can be used also for that purpose. So that brings me to a remark on on testing. So we often collaborate when we sort of do the larger scale implementations. You'll see another one later, but we also have some nice platforms in the lab. So those little race cars that you've already seen in the video and that will come up later. And they're quite fun because you can really test sort of high performance controllers with difficult dynamics, nonlinear, etc. But we also have this electrically propelled system that we can fly outside and test sort of trajectory generation, sort of guidance, navigation, control type of things. We have, maybe I'll play this again, sort of a small scale guided recovery system. So you can control the parachute to do some high precision landing. And so it's really nice to test the algorithms really early on these platforms. They're all developed by Andrea Caron in the team, and we're making everything open source. So hopefully many people can build on these systems or replicate them and build on also the software that we have been developing already. Okay, so now I want to get to the content of the talk. So we wanted not to do the safety filter. That is one that you could combine with any method. But I now want to really talk about specific methods where we directly integrate sort of the safety aspect and do specific sort of instantiations of learning the dynamics, constraints, and the objective. So for the first part, for the dynamics learning, I want to build on a predictive control setup. because it allows us to handle general nonlinear systems, uncertainties. We can directly account for the safety constraints, and we can basically plug in any successful learning technique that we like. So this is our vanilla nominal predictive control formulation, and where we sort of optimizing our trajectory over a finite horizon. So you can also see this in the video here. And then we impose the state and input constraints on the prediction, and we use such a terminal condition in the cost and in the constraints. And then, of course, we know that the sort of the standard formulation has really nice theoretical guarantees. So when we now combine this with learning, we actually have different options, and I just want to point this out. So we can build on the predictive control formulation and integrate learning, or we could also come from a reinforcement learning perspective and just sort of use MPC as a particular policy parameterization. The way that I will talk about this is really in this way, where we build on MPC and integrate learning, but just sort of to highlight that there's really a sort of different perspectives on this. So now when we talk about predictive control, as I said, it's nice that we can build on all of these tools, but of course we also have to be aware that we're solving optimization problems. The good news is that for the last 2 decades, people have thought a lot about how to solve predictive control problems, the structure that they have, and there's lots of tools that allow us to get a high performance implementation. And sort of this list of, it's obviously not complete, but it's extremely nice. So usually you don't have to spend sort of much time on implementing predictive control. Okay, so we want to do dynamics learning. So we could directly learn the entire dynamics model. What we often do, also in view of having to operate the system in the first place to get some data, is that we start with a nominal model. And then we think of learning as really learning the error that we get with the nominal model. But of course, this is not going to be perfect, and there will still exist some residual error, also with respect to the learned model. And what we're interested in, because we want to think about guarantees, is learning techniques that allow us to characterize that residual error. I think there's 2 main routes in which you can sort of characterize the techniques. One is a robust model setting, for example, set membership estimation or techniques building on Lipschitz continuity arguments, where the goal is that we bound this residual error and with some overbound for all states and inputs, could be state and input dependent. Or the stochastic direction, Bayesian regression, Gaussian process regression, where we similarly attempt to bound the error. But of course, because this is a stochastic setting, we can only do this with some probability. But in both cases, we can now actually prepare our method for this error bound, for this maximum error that we can see, and do a robust design. Whereas in the stochastic case, it will only be what we call sort of robust in probability, right? Because the error bound only holds with that probability. So that's nice. And you could say, now I can stop here. But what we actually found is that there's lots of methods to do robust designs, but they often introduce too much conservativeness in the setting, in particular when we have learned models and pretty high uncertainties. So they can be overly conservative. And in addition, when we have process noise and we're really in the stochastic setting, then often the guarantees are rather weak. And so this has motivated us, really the learning setting has motivated us to think about the foundation of predictive control and derive robust methods with reduced conservativeness or stochastic methods that give us rigorous guarantees. And as I said at the beginning, I really don't want to go into these topics today, but just to highlight that also sort of these advanced things, combining learning with control, then motivate sort of new developments at the foundation of control. So in the following, I want to focus on a particular dynamics model. We want to use a Gaussian process to model this error with respect to the nominal dynamics. So what is nice about a Gaussian process is that it's rather general. It's a non-parametric method where we just need to specify the mean and the kernel covariance function, and then we can condition on the data to get the posterior distribution. So quite nice because I basically don't have to think much about the model assumptions that I'm making. So it's very much helpful in the setting where I have a nominal model and there's lots of additional effects that I have trouble characterizing. It's of course not only in control, but also generally in machine learning, been quite successful, and I can directly get the posterior distribution, so the uncertainty. In addition, there's some nice results and bounds that are seeing more and more use, I think, in control, where under regularity assumptions, in a sense, boundedness assumptions, I can derive high probability confidence bounds on my function. So I can define an upper and lower bound based on the mean and the variance that contains my true function with probability 1 minus delta. And I will also make use of such a bound later on in one of the methods. There's quite some motivation for using these, but of course the catch is that they're quite expensive and they scale poorly with the number of data points. There are lots of DP approximations, and we are, of course, everyone's using some, but I think we can actually leverage them even more to reduce the complexity of the GP. Nevertheless, as I'll show in a moment, this is often not quite enough to get them to real-time capability. Over the last years, we've seen some nice demonstrations of DP-MPC that motivate us to take this further. Of course, some older work on autonomous racing that we have done, and also some nice results on drone racing from Davide Scaramuzza's group, where we really see performance improvements, and we can account for the uncertainties, so we're nicely getting uncertainty-aware high-performance control. So what we want to do is we want to integrate such a DP model and the predictive control formulation in order to leverage the improved prediction capabilities of such a model. But we also want to account for the uncertainty. So this makes this a stochastic problem. If I put in such a DP, I can formulate my constraints as chance constraints, also modify the cost correspondingly. But of course, this is not yet a tractable problem. There's many challenges. One is just the uncertainty propagation through going forward over the horizon, because I have to now sort of propagate the DP through the nonlinear dynamics. Then, of course, I have to think about constraint satisfaction guarantees if I now do this in receding horizon and in closed loop. And then I have to think about the computational efficiency, but also the learning efficiency. And I want to address in particular the computational efficiency and the following, and then I'll also show one idea for a really highly efficient parametric approximation that we've done that allows us to learn efficiently. Okay, so for the first approach, we're building on a very common linearization-based approach where we are rewriting the problem and mean and covariance dynamics using linearization. Then we can also approximate the expected cost, and this leads us into deterministic constraints. So this is all nice. We have a nonlinear program. We could go ahead and solve it. But it's actually really expensive to solve. You have a really high number of optimization variables in that problem. And this is, of course, due to the covariance matrices. And you need to, in real time, evaluate the DP posterior mean and covariance. So what we've done is we have developed a tailored algorithm for this problem with the DP in collaboration with Moritz Diel's group at the University of Freiburg. And what is nice is that we can compute suboptimal solutions, but they're still feasible. And so what is the main idea? We built on sequential quadratic programming. And what would happen in sequential quadratic programming is you take this nonlinear problem, you approximate it with a quadratic program iteratively based on the current solution estimate, update, repeat. Now, if we look at the equations, and you really don't have to read them in detail, but what you realize is that the covariance only appears in the constraints. So it's basically tightening the constraints. So the idea is that I could fix the covariance and the tightening at every iteration. So I pull the covariance propagation outside of my QP. And now, different to other heuristics that we and others have used before, the difference is that we're doing this at every SQP iteration. And that actually allows us to relate this idea to something that has been called a zero-order approximation and was done for other MPC formulations, where we can view this as a Jacobian approximation and then analyze the properties. And this allows us to show that it still computes a feasible solution, and indeed, it even preserves some convergence properties if the uncertainty is small enough. And this is, again, really by extending the things that had been done on zero-order approximations before. So this we had done a while back. And so for the last year, the team has really worked hard together with Jonathan Frey and Moritz Steele to put this into a tool that can now be used. And we're calling this L for Arcados. And it's actually more than just for GPs. It allows you now to interface any learning model with Arcados, so with an efficient optimizer, SQP optimizer. And we've particularly also done this for the GPs. And so you can download this, and I think it's really nice. And now hopefully this should become available and people can test this for their own application problems. Here I show this for the cars. So we have our mini cars. We have a motion capture system for the estimation, and then we're solving a model predictive contouring control problem. And what you can see here is just the GP prior, no data. We have high uncertainty, and basically we're just running very carefully along the center line to just carefully collect data. Then we are taking 400 data points of those. We can run with the conditioned GP. You can see that the uncertainty is now reduced, and we're really sort of starting to see more optimal racing behavior. Now you can also do things and learn sort of online. So we're now really taking always 100 data points as we go along. And so over the labs now, sort of you're improving and changing the performance. Okay, so quite exciting. I think for GP MPC, we're at a point where this can be done for a complex nonlinear system in real time. So I think we've made a lot of progress on the practical side. What was nice to see is that from this result that we had to another problem, so this is again this test vehicle at Bosch, it was really simple to do the transition. So what we've done here is we wanted to show that the dynamics improvement when we do a GP learning helps us improve the performance in a lane change maneuver, where previously it was seen that the poor MPC prediction actually led to uncomfortable behavior, a lot of steering action and a sort of oscillation. And with the improved GP model, it was very nice and smooth and really had increased comfort. And so it was very easy now with this toolbox and what we had developed to go into this different application. Okay, so great progress on the practical side. But of course, I think we're not done with the GP MPC. There's lots to do, and this brings me back to the trade-offs between theory, sort of guarantees, computation, and performance. So I think we have methods on both ends. So now this was what I presented. We work with the linearization, very nice practical results, efficient computation, but they can actually under-approximate the uncertainty and so be too optimistic. So it's difficult to give rigorous guarantees for this formulation. We've seen methods on the other end where we get really nice guarantees by sort of over-approximating the reachable sets in an ellipsoidal manner. But this is often really too conservative for practical purposes. So there's lots of room to think about better trade-offs on these different axes. And of course, lots of people working on this. We have recently added sort of one more point in the middle that I'd like to point out. And this is by doing sort of sampling the GP now within the sequential quadratic programming approach. And what this leads to is that we get really good approximations of the reachable set forward, so much, much tighter sets. Of course, the drawback is that it's currently still rather computationally complex. Okay, so that was to think really about the full DP model and the computational efficiency. But of course, I haven't said anything about the learning efficiency. We just took the data that we saw by operating the system. But clearly, you could also now ask questions about exploration. So how do I manage that trade-off? Is it dual control if I'm doing online control, or am I doing this in a sort of an episodic fashion with reinforcement learning? So this is one dimension of thinking about learning efficiency. The other one, and that's what I want to briefly discuss, is to think about how I could use data that I've seen from different but related experiments and tasks to better learn for a new task that I have to execute. So we can phrase that as the problem of multitask model learning. So we're seeing data of different tasks. And what we want to do is we want to learn a model that sort of captures the underlying task structure so that we can, when we see a new task, more quickly adapt to it. So we've worked on a method for this, but then collaborated with the Robotic Systems Lab here at ETH on a particular implementation. And this is for robotic manipulation, because when you're manipulating an object, it's every time different, but of course there's a lot of structure on the task that you're performing. And the specific example that I want to show you is opening a door with this quadrupedal manipulator. So what we were inspired as, so you can, there exists methods that propose multitask model learning with neural networks or full GPs, but we wanted to have something that was super, super efficient and we could put in the robot and would be very cheap in updating online. And so here we were inspired by the sparse spectrum GP approximation, where we're taking an approximation building on trigonometric basis functions. Now, in this multitask setting, our idea is that those basis functions, they reflect the task structure, so they're shared among tasks. And the combination makes this task specific. So in this CDC paper a few years back, we sort of developed a method to do the offline hyperparameter optimization for this. And then for the online adaptation, you can run this really online with sort of recursive estimation techniques. Okay, so that's the setup. We will collect tasks, data for tasks, and we look at different door opening tasks. We're adding different masses to the door. We're perturbing the door by pulling on it. And we again take the structure where we have a nominal model, and then we want to learn sort of the correction to it. So we offline optimize the hyperparameters. Then we get our model, and then we only need to update online and running sort of basically a Kalman filter to update the alphas, the combinations. And what we saw, so here we see a new task never seen in training. The nominal MPC that doesn't adapt is not able to open the door to the desired angle, right? Because it's not learning. And when you perturb it, it also has poor performance. But if you run the multitask MPC, then you very nicely and quickly adapt to a new task, even under these big perturbations that you clearly have never seen before. And also comparing it against single task learning, we see much better generalization because we're not overfitting on one task data set. Okay, so I think also there, a new direction, thinking about sort of learning efficiency and the multitask learning setting that we've started with this work and that we're now very interested in thinking about further. I'll now continue talking about those different learning aspects. And as you'll see, sort of this was the most mature work. So we spent a lot of time working with GPs and sort of doing GP MPC. Now I'm getting into more and more recent work where I'm really just pointing out sort of first results and ideas and also highlighting directions that can be interesting. So when we talk about learning the constraints, then we'll take a slightly different setting. And this is a collaboration with Andreas Krause at ETH. So here we'll assume that we have a system for which we know the dynamics model sufficiently well. So maybe it's a robot that operates slow enough, right? So that I don't have any high dynamical uncertainties. And I have some known constraints, and I have an unknown constraint on the state that's safety critical, and I model as Q of X. Now, what I want to do is I want to learn about that constraint. So I want to explore the domain, but I want to do so safely and in finite time. Of course, unless I make some assumptions now on this problem, I cannot hope to solve this because I cannot hope to learn something about the constraint without violating it. So I will make some assumptions. And this is that we can model the constraint with the Gaussian process. And we'll again assume some regularity on it. So I can utilize my high probability confidence bounds that I've shown you before. Now, if I have upper and lower bounds on my function, and I'm interested in defining a constraint as a super level set, then the lower bound gives me an inner approximation on the constraint, and the upper bound gives me an outer approximation. And of course, if I want to remain safe, then I'm going to work with the inner approximation because I don't want to violate my constraint. So we will work with the pessimistic set defined by the lower bound. Okay, so now I want to learn about that constraint, and I want to learn about it up to epsilon precision. I say that is sufficient. So I need to take samples, and it turns out that a very simple sampling strategy is enough. So I can sample wherever I have uncertainty higher than epsilon. And we can show that this is enough to give us a finite guarantee that there exists a finite number of samples that I need, after which I cannot find another point that has higher uncertainty than epsilon. And this can be done by extending really results that were shown in the literature before to this case where we have a continuous domain. Okay, so that's nice, but now I have a dynamical system. I cannot just, teleport to some sampling location. So I need to think about how to sample safely. And in order to do so, we'll actually now bring back this idea of safety through planning. So if I want to go to some location to sample, and I want to ensure safety, then we'll assume that I have some starting set that is safe, can be small at the beginning. And from there, I need to be able to go to the sampling location. And in order to ensure that I can also stay safe afterwards, there needs to exist a trajectory that brings me back to the set. I actually don't necessarily have to go back, but there has to exist a plan to go back. And so those trajectories, they have to lie within the constraints, but I don't know the constraints. So I'll impose that they have to remain in my pessimistic set. Now I can impose all of these conditions as constraints in a planning problem. So find a location that has higher than epsilon uncertainty, safely go there and safely return. And that gives me a safe strategy. Now I can put this in an iterative loop where I'll start with some safe set, this would be now the true safe set with my constraint so that I can go and return, but I don't know that. So I'll take the current pessimistic approximation of it. I'll solve this optimization problem, which gives me a sampling location that I can go to and return from. So here I've taken a new sample, so I can update my GP modeling my constraint. I can improve my pessimistic approximation of that constraint. I repeat the optimization problem. I get a new sample. I go there, return. I can update my GP, my current estimate of the constraint. And I also repeat to do this. And what we can show is that we convert in finite time, because that was our finite strategy. We achieve safety because of that planning strategy that I described to you. And so we're never actually violating that constraint. And that's true with high probability. And we can actually also guarantee maximum domain exploration. But for this, we will need to make some assumptions on the nonlinear system. In particular, it needs to be locally controllable so I can actually go to the boundary. Okay, so there's various things that I can now do based on this. I could make this even better. Maybe I can grow the pessimistic set if I know something about Lipschitz continuity. I can add a goal to that exploration. So maybe I don't want to arbitrarily explore, but I want to get close to some goal. So I can also impose that as a cost on my planning problem. And this is the most important one. I actually can replan without going back to the safe set. So rather than returning from the sampling location, I can directly replan in sort of a receding horizon strategy and still maintain all the theoretical properties. Here's an example in simulation. We have a car, so non-trivial nonlinear dynamics, and I want to go to that goal. Here's my constraint. I want to learn up to epsilon precision. And now I'm growing also that safe set as I collect more information. And you see that sort of at the beginning that I'll go and now I'll move along that boundary. And starting from here, I'll now move towards my goal. So I can actually do this not knowing about the constraint, but learning about the constraint without compromising safety. Okay, so this brings me to the third part. We've talked about the dynamics and the constraints, but actually the objective is often not so easy to define if I have a difficult problem that I want to achieve. So often it's hard to tune and design. There's many different ways people think about this. You can run sort of black box optimization, such as Bayesian optimization to tune the problem. There's sort of preference-based learning. You can learn about the cost to go. You can also, and this is what I would like to briefly touch upon, think about this as an inverse problem. If I do have an optimal demonstration available, so a demonstration of how I actually want my system to perform. So if I have an optimal demonstration, then my inverse problem describes that from that optimal demonstration, I want to infer what the cost function was that generated this optimal behavior. Of course, inverse optimal control is not the only direction. So this is also addressed in inverse RL. And both have various different methods that have been proposed. I think there's sort of a clear difference between the two directions. So inverse RL is extremely nice because it allows us to naturally consider suboptimality, so suboptimal demonstration, because it builds on an MDP setting. Whereas in inverse optimal control, it's naturally suited to think about constraints. And so when we have demonstrations that were generated in a constrained environment, that allows us to take that additional information into account. And that the idea is that this leads to better estimates. While, of course, you can also approach this from the inverse RL side, what I want to show you is that we can try and approach this from the inverse optimal control side. So we want to extend the methods that we have to deal with noisy or suboptimal demonstrations. And so for this, let me just briefly tell you how inverse optimal control works. It builds on the optimality conditions, the KKT conditions. that are necessary under suitable assumptions. So we can write down stationarity, complementary slackness, primal and dual feasibility, and we'll for now assume that my demonstration at least are primal feasible. So this is usually satisfied. So now I can actually solve this system of equations given an optimal demonstration x star and u star. So I can solve for the dual Lagrange multipliers. And if I propose a parametric form of my objective function that I don't know, I can also solve for theta, so the parameter. So that's quite nice. But of course, if I now put in a suboptimal demonstration, any one of those optimality conditions can actually be violated. The way that this had been addressed in the literature is that we relax the stationarity condition. So we keep dual feasibility and complementary slackness. We assume primal feasibility is given, and then we relax the stationarity condition and take the least squares approximation. However, this is actually an inconsistent estimator if we have a noisy demonstration. Let's say if I have a noisy demonstration, there exists an optimal demonstration plus some noise, then this can be seen by rewriting our stationarity condition as a regression problem. So here we have a Jacobian, which will be a function of the input sequence. Here's our parameters that we're optimizing for, and this should equal to some output, which in this case is 0. But in this case, we actually have an error on u, which is the independent variable, and not on y. So actually, this is an errors and variables problem, and so a least squares estimator is not consistent. So this was a nice realization, and we then just started using regression techniques from error and variable regression. We've tested 2 different directions, one where we assume the noise is Gaussian, so we can solve sort of a maximum a posteriori problem, one where we say we don't know anything about which distribution this is, and then we can write this as a total least squares problem. And what we saw is that for different sort of simulation settings, a linear spring damper system, kinematic bicycle model, a Bayesian glucose model, which is really then sort of the second setting, we get significantly reduced estimation errors by writing this as an error and variable regression problem compared with sort of the least squares relaxation. So that's quite motivating. So these techniques give us consistent estimators under certain assumptions. We can sort of reflect the quality of the estimate. But of course, there's a big drawback, and this is that we have the remaining KKT conditions in the constraints. So it is a difficult optimization problem to solve. It's a problem with complementarity constraints. And that's, of course, not easy to solve. Nevertheless, so we're continuing to think along this direction, but we've also taken a second track that is maybe a little bit more practical, and where we sort of go back and think about the original relaxation, and if that's actually the right way to formulate the problem. And we've come up with a different relaxation that is based on a soft constraint formulation, which gives us sort of a very nice way to penalize constraint violation. So this is coming up soon, so stay tuned. Hopefully we'll put the paper out soon. Okay, so that brings me to the end of my talk. So what I was hoping to show you is different flavors of how we can combine learning and optimization-based setting of control. But first, we started just by defining safety. And we did this through defining it as a forward planning problem. So we can plan a backup trajectory, and that gives us a safety certificate. And it's a very general idea. Then we talked specifically about Gaussian processes and how we integrate that in predictive control. And I've shown you a tailored optimizer that you can all use. We've talked briefly about multitask learning for approximate GPMPCs, or we would take a parametric approximation of it. We then went and away from the dynamics and thought about constraints and how we can actually safely explore an unknown constraint. And then lastly, we talked about inverse optimal control under suboptimal or noisy demonstrations. And as I said, so in particular, those later topics are really sort of first attempts towards addressing a problem. And clearly, at the end of the day, we will have to think about integrating those three directions where we potentially have uncertainty in both the dynamics, the constraints, or the objective. And the goal would be to integrate these towards really then achieving sort of safe autonomy. Great. So with that, I'd like to thank you all for your attention. Apparently there were no urgent questions in the meanwhile, but let me now see if any questions have come up.
Thank you so much, Dr. Zeilinger. And yeah, we have a couple of questions. I'll just let you know. So the first question is for online policy determination, how much time it takes to do the learning part, and what are the computational requirements for this online learning?
Okay, so I think what I've shown you in the demonstration, so we have to run this at below 30 milliseconds. And what is the most expensive part is really running the optimization. Of course, you also need to prepare the problem, etc. And there's some time involved for this, but really the majority was to solve the optimization problem. Of course, this changes depending on what you use. And so in this tool that I described, so the way that we interface now Akados with different models is via their sensitivity. So you can use your general favorite tool. In our case, we use GPyTorch. And now interface this with Akados, so you can leverage really the fast learning evaluations also with the fast optimizers. I hope that goes in the right direction.
Thank you. And the next question is, how can we collect the data to learn the constraints? Which means, is there any way we can get the output of the constraint function if it is unknown?
Yeah, exactly. So that's why I said at the beginning, if you don't make any assumption, then it will be very difficult to learn something about the constraint and be sure that you're not violating it. But our DP assumption basically means that we learn something about the constraint if we're close enough, right? So if we're getting close to the constraint, we already learned something about it because of the correlation between points that we're assuming basically by modeling this as a GP. And so that's how we can actually learn without violating the constraint. There's other models that you could take, but I think that's sort of in essence the property that you're looking for is that you can learn about Q of X, or the unknown constraint, before actually hitting it.
Thank you. And another question is, how many demonstrations do you typically need to make the inverse optimal control problem work?
So that, of course, depends on how uncertain or how suboptimal you are, how much noise you have. In the unnoisy case, you only need one. But then, of course, if you have noise, then the more demonstrations you have, also more information. But in the results that I've shown you, it's really small numbers. So I would have to look up exactly how many, but I want to say less than 10 demonstrations that we use. But I would have to go back and see this exactly. But it's really not that many that you need.
Yeah. I have one question. Like, it is really interesting how, I guess, in case of trying to obey these unknown constraints, and I guess it's some sort of hosting inequalities and these things. that we've used, and I've typically seen people in RL use these confidence or like these concentration inequalities to implement optimism, and it's interesting how you've implemented pessimism to satisfy safety guarantees. And yeah, that's really good. But on the whole, like if if we look at safety critical applications like healthcare, and in such systems, uh, how how all right is it to give them these probabilistic safety satisfactions, like looking at like a high level perspective? Because when it
Hmm.
comes to medicine and let's say treatments, people might not be susceptible, or like they may not be okay with agreeing to such explorations, pessimistic expectations. Like
Yeah.
how do you address this issue? How
That's a
should one
great
address?
question. Yeah, and I'm really just learning about this because I'm also not an expert on the medical side, but we've been discussing with experts. And interestingly, what is actually in many problems okay is some zone in which you have to keep a certain value. So it's often not that this is exact tracking of some set point that is important, but there's some physiological range in which you have to keep the system. Um, and so, given that, it's actually fine to think about this. So, you don't have to be super precise, and the high probability result would be acceptable. But of course, there's certain critical values that you really shouldn't
Yeah,
exceed. Um, so, I think a combination of really robust bound that is then bigger combined with sort of a physiological zone that you really want to achieve might be a good way to go. But this is something that we're really also just currently discussing and trying to find a good problem formulation for.
yeah. Thank you so much. Yeah. And there's one last question if you
Mhm.
have some. Yeah. Could you please elaborate on key strategies for enhancing the computational efficiency in the proposed learning-based MPC framework?
Um, Sorry, so can I elaborate on how we make this more efficient? Was
Yes,
that the question?
yeah, they'd
Okay.
like to know the key strategies for enhancing computational efficiency.
Mhm.
Just high
Um,
level.
Okay, so in what I presented on the GP and PC, the key was really, in a sense, to get rid of the covariances at every iteration, um, but systematically analyzing the error that you're making by doing this. So I'm not getting an exact Jacobian anymore. And so I have to make sure that with this approximate Jacobian, I'm still fine in my iteration. So that in essence is how we simplified it. And that can, of course, be different for different methods, but similar approximations can make sense. And then for the efficiency with different learning models, and I think I sort of mentioned that before, it's really sort of when you're running SQP, then sort of your model information is really coming in through the sensitivities. And so you can now nicely interface sort of your iterative optimizer by just feeding it the right sensitivities at every iteration from your model, and that formulation then allows you to use the efficiency on both sides. So I think it's both. So it's a good interface, and it's an efficient optimizer that is sort of goes through approximate iterations.
I think that's all the questions we have for today.
Okay,
Yep.
wonderful.
Yep. Thank you so much for giving this talk. It was wonderful and it was amazing.
Thank you again for having me.
Yep. Like this.
Have a nice day. Bye bye.
Thank you. Bye bye. All right, everyone. See you next week. Bye bye. Bye bye, Dr. Zeilinger.